Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at the mean value theorem. So it says that if you have a function that's continuous and differentiable on an interval, then this holds. We read this as there exists a c between a and b, so part of the interval, such that fb minus fa over b minus a equals f dash c. What is that talking about? Well, hopefully you recognize this as the formula for the average rate of change. fb minus fa over b minus a is precisely the gradient of the secant that goes through the curve at x equals a and x equals b. So this is the average rate of change of the green function between those 2 points. Now f dash c is the instantaneous rate of change of the function at some point where x equals c. So what we're going to have a value c between a and b, and if I draw the tangent to the curve at that line, these two lines here are parallel. So the mean value theorem is an existence formula. It just says that such a point c exists, not necessarily how to find it, although finding it's not too hard. So at this point, the gradient is equal to the average gradient or average rate of change between A and B. So as a practical example, the mean value theorem is used in point cameras that measure your speed between 2 points, like the ones on Hindmarsh Drive. So if you travel, say, 10 kilometers in 8 minutes, your average speed is 75 kilometers per hour. The mean value theorem says that there must have been a time where your speed was exactly 75 kilometers per hour, and that's how they get you with the cameras. Now, Rolle's theorem is kind of like a special case of the mean value theorem. It's just when FB and FA are equal. So what that means here is this would be 0. You'd have a horizontal gradient, and therefore this would be a stationary point. So for Rolle's theorem, we have a function like this. FA equals FB, so their y values are equal, so the secant between those 2 points is horizontal, and Rolle's theorem is just saying that there will be another point up here where the tangent is horizontal, and of course horizontal tangent means it's a stationary point. Alright, let's look at a couple of questions now. Find the value c that satisfies the mean value theorem for fx equals the square root of x minus 2 between these two values. So what we're going to do is calculate first the left-hand side of the equation on the previous slide. So f11 minus f of 6 all divided by 11 minus 6. So f of 11, 11 minus 2 is 9, square root of 9 is 3. And then f of 6 is 2, because square root of 4 is 2. It's 3 minus 2 over 5, or 1 over 5. So that is, what I've just calculated, is the average rate of change of this function between the points 6, 2, and 11, 3. So the mean value theorem says that between these two values there must be a value c, so that the gradient of the tangent at that point is also 1 over 5. So let's differentiate x minus 2 square rooted. So we know that we can write that as x minus 2 to the power of a half, and we can use the chain rule. So we move the power to the front, decrease the power by 1, and we normally times by the derivative of what's inside, but the derivative of what's inside is just 1. So this is equal to 1 over 2 root x minus 2. So we're told there will be some x value between 6 and 11 such that this will equal 1/5. So of course, if these two are equal, they have equal numerators, then they must have equal denominators. So we have 2 equals 5. Divide each side by 2, we get square root of x minus 2 equals 2.5. Now we're going to square both sides. We get x minus 2 equals 6.25, x equals 8.25. So at x equals 8.25, the gradient of the tangent is 1/5, which is equal to the gradient of the secant that passes through the curves at the points 6, 2 and 11, 3. All right, let's look at an example now involving Rolle's theorem. So we're going to find the value of c that satisfies Rolle's theorem for this function here on this interval. So note here that f of 0 and f of 4 are both equal to 0. So when you have the function take the same value at different points, then you can use Rolle's theorem as long as the function is continuous and differentiable, which polynomials always are. So I'll just point out it wouldn't matter if this was a different value. It wouldn't matter if this was 2, Rolle's theorem would still apply. All we need for Rolle's theorem is the function at different points taking the same value. So because of this, we know that there will be a stationary point on this interval between 0 and 4. So let's find out where that is. So f dash x derivative will be 3x squared minus 8x. So if I want to find out where that derivative is equal to 0, I can take out here a factor of x. So I get 3x minus 8. And so if the derivative is equal to 0, either x equals 0 or x equals 8 over 3. This function has stationary points at x equals 0 and 8 over 3. So x equals 0 was one of the endpoints of the interval, so we're not including that because 0 is not really between 0 and 4. This is our value here. There will be a stationary point at this point, and that is the value of c that makes the equation on the first slide true. All right, let's now look at using the mean value theorem in a proof. So we're going to use the mean value theorem to prove that tan x is greater than x for x between 0 and pi on 2. So when you're doing this, don't jump in too quickly because you might think, okay, well, what we're going to do is evaluate tan at the endpoints. So like tan of pi on 2 minus tan of 0. But that's actually not going to work. Reason, tan of pi on 2 is not defined. But because I want to end up with tan x as an x, let's just put in an x. So x is just going to be some number between 0 and pi on 2. So we have tan x minus tan 0 over x minus 0. So that's the left-hand side of the mean value theorem, the average rate of change. And at some point, that's going to equal the instantaneous rate of change. So what is the instantaneous rate of change of tan x? Well, what we would have to do is differentiate x, which is sine x over cos x. So hopefully you know that that's sec squared x, or 1 over cos squared x. Okay, so we know that cos x is always less than 1 between 0 and pi on 2. In fact, more precisely, cos x is between but not including 0 and 1. The inequalities here are strict because x can't equal 0 or pi on 2. So that means if you square it, if you square a number between 0 and 1, you get another number between 0 and 1. So if this is between 0 and 1, this will be more than 1. So we can rewrite this as tan x minus tan 0. Well, tan 0 is just 0. Tan x over x is greater than 1. And that's because this here has to be greater than 1. So then I can simply multiply each side by x. I don't need to worry about reversing the inequality because x is positive. So I get tan x is greater than x, and I've proved what I meant to. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.